Right, so now with our system defined correctly, sorry guys, I just have to get my pen. So before we had this system here, now that it's defined correctly, there's one last thing we need to do. First of all, I want you guys to note the use of the differential equation in the second equation, okay? And we can also convert the initial conditions over to the new functions for x1 and x2. So the way we do that is by recalling that since x1 represents y, that means x1 of 3 is going to equal y of 3, which was the first initial condition, right? Since we let x1 of t equal y of t, therefore their initial conditions will also be the same. And the output of that was equal to 6. Okay? Likewise, we can say x2 of t, or excuse me, x2 of 3, excuse me. We know what this is defined as. x2 of t is equal to y prime of t. So this is going to be equal to that initial condition, which was y prime of 3. Okay? And that's going to be set equal to minus 1, like so. All right, so this problem is almost done. All we have to do now is put this all together to give us our final answer, which is the system of differential equations. So wrapping this up, the way to write out a second order differential equation as a system of first order linear differential equations using the change of variable techniques we just discussed would give us the following answer. It would be x prime of 1 equals x2. Okay, so that's the key change of variable that we performed at the very beginning. And also, x prime of 2 is going to equal minus 1/2 x1 plus 5/2 x2. And there we have it. You know where this comes from. We just derived this, and this comes from the definition that we created with the change of variable. But this problem is not quite done yet because it hasn't been turned into an IVP, a correct IVP. So the way we do that is by looking above to the conditions we just created and just write out the IVP, which would be x1 of 3 equals 6, right? And x2 of 3 equals -1. And that's it. So now we have successfully converted that second order differential equation as a system of first order linear diff EQs. All right, so that's a good warm-up example. Now let's jump to a more realistic example as something you and I would be very interested in converting to a set of first order diff EQs. It would be the following problem, which is going to be in this case a fourth order diff EQ. Okay, so in this example, we're being asked to do the following. Write the following write the following fourth order differential equation or diff EQ. Sorry about the pen here. Okay, as a system let's see, of first order linear differential equations. or diff EQS. Okay, so the example is going to be the following. It'll be y4, this stands for the fourth derivative, plus 3y double prime, second derivative, minus sine of t y prime, okay, plus 8y, let me go ahead and erase that, make it a little better, 8y equals t squared, okay? And then there's some initial conditions that go with this as well, and you'll need not just one, not just two, but 4 initial conditions, okay? And they are y of 0 equals 1, okay? Y prime of 0 equals 2, all right? Y double prime of 0 equals 3, and the last one, which is going to be y triple prime of 0 equals 4, okay? So in our next video, I'll show you guys how to create the change of variable that we need and define 4 new functions, and then how to rewrite the system to effectively get the unique system of first order linear differential equations that would simplify and allow this first order system or equation to be solved much more easily. Stay tuned.